Morning. Good morning to everybody. We will revise the synapse today. This is the synopsis of the lecture. Now, to define the synapse, essentially it is a physiological junction between the two neurons. So, what it says is there are two neurons and there is a junction between them, and this is physiological. So, it happens to be the way of functional contiguity between two neurons, but there is no anatomical continuity. There is no anatomical continuity, but the continuity that occurs is functional. So, you use the term contiguity between two neurons. So, the transmission of impulse occurs across the synapse in a certain mechanism, not directly, but in a certain mechanism. Now, if you see, there is a presynaptic neuron and a postsynaptic neuron. That means before the synapse, there is a presynaptic neuron, before. And there is another after synapse, postsynaptic neuron. So the junction is in between them. So one thing more, this diagram shows you that there are plenty of endings with the synapses on a neuron. On this neuron, there are plenty of synapses that it has received. Similarly, one neuron also supplies several neurons. This is what you call convergence, and this is what you call divergence. They are essentially the chemical synapse that are very prominent in the mammals. Occasionally, you also may have electrical synapse. Electrical synapse are more common in the lower animals. Okay. So, if you look at the physiological anatomy, there is a presynaptic part and there is a postsynaptic part. So, in between there is a synaptic cluster. So, there is a presynaptic terminal, then you have a postsynaptic part. I will come to the details little later. You can see the mitochondria in the presynaptic part, channels for the calcium, which come to that activity, and then an action potential that arrives. Now, there are plenty of vesicles, what you call synaptic vesicles, and contain neurotransmitter which will be released into the synaptic cluster, and it is dissipated. It travels across, diffuses across the synapse, and reaches the postsynaptic part, and produces an effect through the receptors. Could be ionotropic or metabotropic. We'll deal with it a little later. Now, if we look at the electrical synapse, the junction is quite close. The gap between them is very small. And then we have gap junction, which are low resistance bridges. So the electrical change that has come down up to this portion, in the way of action potential, can cross to the postsynaptic part, to the gap junction. There is no such intermediary like the neurotransmitter. And this neurotransmitter mechanism also makes it that the transmission is one way, presynaptic to postsynaptic. But here in the electrical synapse, it could be both ways. The classification can be according to the location of the synapse: axosomatic, axodendritic, axonic, rarely dendritic, which is rare. Now, this is according to the way the parts which are participating in the synapse. So if you look at this diagram, and 3 neurons here is a more simplified version of what you see in the other 3. So you can see this is the presynaptic signal of presynaptic neuron, and that is ending on a postsynaptic dendron or dendritic spine. So this is axodendritic. Now the axon terminal can also be making a contact with the postsynaptic cells soma. So this will be axosomatic. And we have another type which we call postsynaptic, the axonal type of synapse, where this is the primary part. So the presynaptic neuron, postsynaptic neuron, and on the axon of the presynaptic neuron, you find that another axon terminal is ending. So this is an axon, and this is also an axon. So you call this axonal. You often see this in the synaptic inhibition. So this is what is the description that we have just now said. So actually the dendritic synapses are more common, and even soma also receive a large number. So axodendritic synapses you can find in the motor neurons of the spinal cord, excited synapse in the cerebral cortex, surrounding fibers in the cerebellum, etc. Axosomatic synapses you will find in the motor neurons also again, and then there in the spinal cord, motor neurons of the spinal cord, basket cells of cerebellum, and autonomic ganglia. Axonal spinal synapse is mostly in the spinal cord. Dendrodendritic synapses between mitral and granule cells in the olfactory bulb. So this is relatively rare. Now, you can also classify according to the type of transmission. It could be excitatory or inhibitory. If it produces an excitatory postsynaptic potential, that is a depolarization change, then it will be excitatory synapse. And if it causes hyperpolarization of the postsynaptic, then you call it as the inhibitory postsynaptic potential, which is a hyperpolarizing potential. Now, depending on the neurotransmitters, essentially you can use the name of the transmitter and say ergic. Cholinergic, acetylcholine is the transmitter. Norepinephrine is the transmitter for most of the adrenergic terminals, mostly most of the adrenergic terminals. And you also have other adrenergic terminals which have the neurotransmitter other than norepinephrine, like epinephrine, etc. Histamine, etc. are also adrenergic. Dopamine, these are all adrenergic. So other than acetylcholine, epinephrine, serotonin, dopamine, histamine, gamma-aminobutyric, butyric acid, lysine, glutamic acid, aspartic acid, and cabalins, nitric oxide, and other less known neurotransmitters. There is a large list of neurotransmitters available, but lesser number of places that they active. Then, if you look at the anatomy of the synapse, which we have touched a little bit, then you can see the presynaptic neuron with the terminal. That is the axon terminal. We also call it as terminal bouton or button. Actually, this word is a French word, so that's why it is written like this. So it essentially means button, terminal button, or terminal bouton. Synaptic knobs, synaptic knob, axon terminal, synaptic terminal, terminal button, whatever. These are all the same. They are all referred to the same base. And most of them are excitatory, some are inhibitory. And you will find about 10,000 to 200,000 synapses on a spinal motor neuron depending on the spinal cord. So a large number is available. So and postsynaptic neuron dendrites are soma mainly. synaptic nerves end on dendrites mostly 80 to 95, and then some 5 to 20% on soma. So dendrites receive most of the information in the postsynaptic part. So if you look at the structure, axon terminals end at the synaptic knob or terminal beacon. They have the synaptic vesicles at this place, at this bulged portion, like the mitochondria empty, and from the axon part you see some neurofilaments. These are for the sake of contraction or movement of this content. And there are here microtubules. So they will transport substances from the soma to the axon terminal. Then the presynaptic membrane is this, that belongs to the presynaptic neuron, and the postsynaptic membrane belongs to the postsynaptic neuron. In between, we have synaptic cluster, about 20 to 40 nanomicrons. Then, of the postsynaptic membrane, what is in contact with the presynaptic part is called as the subsynaptic membrane. We also call the synaptic part, which is actually taking part in the synapse, we also call active site. So presynaptic part, axon terminal, synaptic knob contains mitochondria, synaptic vesicles with the neurotransmitter membrane, synaptic knob contains voltage-gated channels. So here you will also find voltage-gated channels. So calcium channels will be affected whenever there is action potential coming to that part. Presynaptic membrane is actually taking part in the synapse. Ratio between synapses to a postsynaptic neuron, average about 1 to 8,000. Can be a few as much as a few to 200,000. Then 1 to 1 ratio is found in the midbrain, 1 to 10,000 synapses to 200,000 synapses and neuron. And in the forebrain, we have about 1 to 40,000 in the forebrain. So the ratios may vary from place to place in the nervous system. Postsynaptic part, synaptic cleft is the gap between the presynaptic and subsynaptic membranes of synapse, 200 to 400 axon units in the thickness of the synaptic cleft, or rather the space in between the subsynaptic and the presynaptic parts. Subsynaptic membrane contain the receptors. They could be inotropic receptors or metabotropic receptors. Inotropic receptors will bind with the neurotransmitter and then associated with the ionic channels, gated ionic channels, sodium and potassium. And generally sodium due to the excited synapse, and potassium if it is inhibitory channel. The metabotropic refers to the second messenger system in the postsynaptic part. So when a neurotransmitter comes, it binds with the receptors, and then that causes the activity associated with the second messenger. And the second messenger is the one which produces vitality change. So synaptic transmission and the action potential propagation in the presynaptic neuron axis. So it has come to the synaptic knob. So when it comes to synaptic knob, you will find the voltage-gated calcium channels are opening, and so permeability to the calcium is increased at the active zone of the presynaptic membrane. Calcium enters from ECF, extracellular fluid, into presynaptic. So from outside into the inside, the calcium enters. Then the calcium concentration increases in the synaptic knob. This calcium mediates exocytosis of the neurotransmitter. So calcium causes the contraction of the microfilaments, and that causes the movement of the synaptic vesicles towards the membrane, presynaptic membrane, and then attach to the presynaptic membrane and open up and release the neurotransmitter by exocytosis into the synaptic cleft. So basically, it's recovered into the presynaptic kernel by endocytosis, the reverse process. But to exocytosis, it comes in synapse. To endocytosis, it goes into the presynaptic part again, and it is reutilized also again. The quantity of neurotransmitter released is directly related to the number of calcium ions that are entered. So more calcium ions entering, more will be the neurotransmitter release. More will the neurotransmitter release, more will be the chain, electrical chain of the postsynaptic potentials. We can excited, we are individual. So synaptic vesicles, they know and trying when the action potential, right? So calcium influx facilitates the fusion of vesicles with the presynaptic membrane. Not only that, they move the synaptic vesicles toward the presynaptic membrane, and then they also the fusion as well. Fusion of synaptic vesicles and presynaptic membrane is facilitated by something more as well. The proteins like synaptobrerin, syntaxin, SNAP25, SNAP alpha, and gamma. Now we'll see what are they, where are they present. This synaptic vesicle, and these red dots are neurotransmitters. Now, the synaptic vesicles are moved towards the synaptic membrane because of the calcium. Now that is accumulated inside the synaptic nerve portion. Now, this will also be attached with the postsynaptic, the presynaptic membrane. Synaptic vesicle membrane is to be attached to the synaptic membrane through synaptobrerin, and syntaxin. Synaptobrerin is with the synaptic vesicle. Syntaxin is with the presynaptic membrane. Now you also find the SNAP alpha and gamma are associated with the synaptobrerin, which will facilitate the action. The SNAP25 is associated with syntaxin. So mainly these two, and then also facilitated by these two proteins, which are snare proteins. The synaptic vesicles, they get attached with the synaptic membrane. And then what will happen? When they attach, they open. And exocytosis occurs. But then what happens after that? So once the neurotransmitter goes out, what happens? Vesicle after discharging its contents. Discharge of granular content into synaptic cleft by exocytosis, this you know. The vesicular membrane then is coated with a substance called clathrin. So clathrin is coated over this vesicle, which is empty. So that is first. And this causes endocytosis. That means whatever is coming, if the vesicle is coming out, it should also take it. So whatever it is not going away. So the vesicle, which is emptied, is still the synaptic nerve. Now, because of that clathrin. Then diffusion of neurotransmitter across synaptic cleft vectors, etc. Before that, we see clathrin is released. When the clathrin is released, the membrane of the synaptic vesicles forms, become early endosome. The part is early endosomes, and these early endosomes form the vesicles, and the vesicles are filled with the neurotransmitters. So diffusion of the neurotransmitter across synaptic cleft will have occurred to reach the postsynaptic pump. Binding of the neurotransmitter with the receptors in the synaptic membrane is the next step. So the inotropic receptor, there are inotropic and metabotropic receptors on the postsynaptic membrane or subsynaptic membrane. Then the inotropic receptors, they cause the opening of the ionic channels, either the sodium or the potassium. Sodium ion channels for the excited and potassium for the inhibitory. Change in the postsynaptic membrane potential occurs, either excitatory or inhibitory. So if you see this neurotransmitter that is exocytosis, then the neurotransmitter come into synaptic cleft, diffused across synaptic cleft, bound to the receptors. So ionotropic receptors open the ionic channels. Ionic channels. Then for the calcium directly. The other, which are metabotropic receptors, here the channels are not open, and they, as the receptor binds with the metabotropic receptor, that causes the activation of the second messenger, and this second messenger will further initiate the series of events that will come into action, producing what change is to be brought about. So once either the ions, sodium ions coming in or potassium ion going out, whatever, that causes the change in the membrane potential. There could be a series of biochemical reactions. It is also possible that the regulation of gene expression, particularly through this metabotropic receptors. So neurotransmitter concentration, we said that determines the amplitude of the potential that occurs in the postsynaptic part. More action potentials in the presynaptic fiber at the synaptic terminal. More entry of calcium ions into the cytosol in the presynaptic part. This causes more synaptic vesicles to move towards the presynaptic membrane. Then finally, neurotransmitter is released. So the more synaptic vesicles, more neurotransmitter released, more receptors are activated, more receptors are activated, more change in the membrane potential, plus this subsynaptic. So the action potential here that has come to the synaptic terminal is bringing a series of changes. Ultimately, the membrane potential of synaptic membrane thus producing a postsynaptic potential, exactly. And finally, at the initial segment part of the postsynaptic neuron, the action potential starts when the membrane potential, the synaptic membrane potential reaches the threshold. Rather, excited postsynaptic potential reaches the threshold. Then the action potential will be generated in the beginning portion of the postsynaptic neuron. So diffuse across synaptic cleft binds with the specific receptor, subsynaptic membrane to produce EPSP or IPSP, destroyed by the what is happening to it? Fate of neurotransmitter. After this, destroyed by the specific area. It will get acetylcholinesterase. Correct. So it is also possible reuptake into the synaptic knob also occurs. Some may bind, that is, some is destroyed, some is taken up by the presynaptic axon, and some may bind the presynaptic receptor to regulate neurotransmitter release. So what enters will be used for resynthesis of the neurotransmitter. And here, this is used for regulating the presynaptic part, presynaptic part. Excitation of subsynaptic membrane. So once the ionic channels is open by increased permeability of sodium molecules. Also possible is calcium ions. So sodium moves into the postsynaptic cell, depolarization occurs. So depolarization is the excited postsynaptic potential, and then when this reaches the threshold, then at the initial segment of the postsynaptic neuron, you will get an action potential. Why? Because the low threshold of that area, low threshold of the area, that's about 10 to 15. So inhibit the subsynaptic membrane. Here, the combination of the neurotransmitter inhibit neurotransmitters with the receptor will cause potassium channels or chloride channels to be open, mostly potassium ion with the channels. So, simultaneously, the permeability to sodium also will decrease, and impermeability of sodium also occurs. So, potassium effects are calcium, chloride ion influx will lead to more positive charges outside. So, more negative charges inside, so that becomes hyperpolarization. This the more negative charges inside is hyperpolarization. Inhibitory post-synaptic condition. So, when the hyperpolarization occurs, now the potential change should occur to reach the threshold is increased. You can see it is increased compared to from here to here. From the resting membrane level is only this much change, 20, let's say about 20 millivolts. But then if there is hyperpolarization, would say another 10, so 30. That is a bigger difference. So it takes, it becomes more difficult for the EPSP to be produced. So anyway, they will summate the actions of EPSP and IPSP will summate, and only when the threshold is reached, then the action potential is produced in the initial segment. So this inhibitory Golgi bottle neurons and glycine, Golgi bottle neurons, they have the transmitter as glycine. Action potential postsynaptic neurons. 10 to 15 millivolts is of depolarization. Then it occurs at the axon length, the initial segment of the axon length. So that is the axon length is at the beginning of the axon, where it is continuing from the soma. So spike potential between 30 to 40 millivolts, then you find action potential continuous with the fiber. Depolarizing and hyperpolarizing levels are integrated, and finally, when integrated, summated, when depolarization is about 10 to 15 millivolts, the spike potential is neurotransmitter substances vary from synapse to synapse. Now, it is not that only one type of neurotransmitter is present in synapses, but in a given synapse, there is only one type. A given specific synapse will have only one type of neurotransmitter. And then the different synapses will have different neurotransmitter substances. So that is the variation. But the same neurotransmitter is always released at the given synapse. Okay, that won't change. So the synapse response also will not change. It will be the same response that is produced when the receptor and the transmitter combines. So if it is an excitatory effect, same excitatory effect is produced every time. With inhibitor, same inhibitory effect is produced every time. Hence, the given synapse is either always excitatory or always inhibitory. Glutamate, aspartate always induce excitatory postsynaptic potentials. Glycine and GABA always induce inhibitory postsynaptic potentials. Others may do both. You'll find norepinephrine and acetylcholine, they have this kind of action. For example, if you look at the action of acetylcholine on heart, it causes inhibition. You use acetylcholine on small intestinal wall, smooth muscle, that causes that also will cause the same thing. That will also be acetylcholine at the heart causes inhibition, but on the intestinal wall it causes the contraction. Similarly, norepinephrine activates the cardiac muscle and causes the relaxation of the smooth muscle of the intestinal wall. Neuromodulators. Earlier we were talking about the neurotransmitters. These are rapidly acting small molecules and they are packaged in synaptic receptors. The axon technology. Neuromodulators are large molecules such as neuropeptides and synthesized in soma and they come down from soma to the axonal terminal to the microtubules. They are packaged into dense core vesicles present in the axon terminals. Typically, an axon terminal releases only one classical neurotransmitter. No more than one neurotransmitter is released by one axon. Same terminal may also contain one or more neuropeptides that are co-secreted along with the classical neurotransmitter. So, neuromodulators could be more than one, but they are really in smaller quantities. Neuromodulators diffuse locally and act on other adjacent neurons at much lower concentration than classical neurotransmitter. Neurotransmitter is released in a larger quantity because from the synaptic vesicles it is coming in larger quantities, but the neuromodulators is a smaller concentration, but it goes into the nearby neurons and they cause the effect. And so they are slower and the action is very prolonged. Some neuropeptides may act as neurotransmitters also, but most are neuromodulators. Neuromodulators bind to neuronal receptors at non-synaptic sites. So there is no synapse for the neuromodulator. Okay, though it is from the presynaptic terminal they are released, there is no synapse for them. May act on the pre or postsynaptic neurons, either of them do not cause EPSP or IPSP. But what they do is they bring about a long-term change. It may be for days or 2 years, and subtly modulate either by inhibiting or depressing or enhancing and activating synaptic effectiveness. Some may also have a hormonal role in other parts of the body. You call it a hormone when it goes into the blood and goes into other parts of the body. So what are the, we will also see some properties quickly. So here you can see one-way conduction, well-measured law of synaptic delay, excitation of postsynaptic neuron, inhibition of postsynaptic neuron, then convergence, divergence. Up to here, you are more or less familiar. Summations, we will talk about this using a picture. Subliminal fringe and occlusion, similarly we will do so. And facilitation, reverberation, synaptic laxity after discharge, susceptibility to hypoxia, synaptic fatigue or habituation, Renshaw cell inhibition, presynaptic inhibition. We all these things will see. Law of one-way conduction or forward conduction. Always, because the neurotransmitter is present only in the synaptic vesicles of the axon terminal of the synaptic part, it can be the neurotransmitter can only be released with the presynaptic terminal to the synapse and cause the effect on the postsynaptic. So it is always a one-way conduction. Because one more thing you can say here, you stimulate a sensory part and the corresponding motor neuron can be affected. But you stimulate the motor neuron, it doesn't do anything to the sensory neuron because the other way, the reverse way, the transmission cannot occur because the postsynaptic neuron will not release any neurotransmitter to the synapse or to this part. So it will be a one-way traffic, a law of one-way or forward conduction. Bell-Megendy's law. Bell-Megendy law essentially says the dorsal root ganglia contain the sensory neurons and so on, while the dorsal root ganglia contain the sensory part and the sensory sensory neurons, and then the ventral root is the axon of the motor. Okay, so from the sensory to the motor only is possible. It cannot be from motor to sensory. Then, because neurotransmitter is present only in the presynaptic nerve terminals, whereas postsynaptic membrane contains the receptors for neurotransmitter. This is possible, and it cannot occur in the reverse direction. The well-measuring data. Dorsal nerve root is sensory, ventral nerve root is motor. Simple. Synaptic delay. There is some delay that takes the transmission to occur across the synapse. And that time lapse is called synaptic delay, and this is about 0.5 milliseconds. From the synaptic delay, you can estimate the number of synapses included in a reflex. Then, due to release, the reasons for the synaptic delay is the release of neurotransmitters, diffusion of this neurotransmitter across the synaptic cluster. Then neurotransmitters will have to bind with the receptors, and the ionic channels will have to be open, and these diffusion ions across the membrane, they have to go across the membrane, and across the membrane, these ions will have to go across the membrane to produce the EPS. So the series of activity will have to occur before the excited postsynaptic potential or inhibitory postsynaptic potential is produced. So you have a synaptic delay, and there is about 0.5 milliseconds. Significance is more synapses in reflex, longer the latent period to produce reflexes, to produce the reflexes. And properties of convergence and divergence, we have talked about this. You can see this neuron is receiving so many inputs. That is, so many inputs are converging. The same neuron can supply several neurons. So this is diverging the supply to several neurons. So the same thing, you will see this is convergence and this is divergence. Now, you pay attention about the summation. Summation can be temporal summation or spatial summation. Okay. So what is temporal? It is time related. Spatial, space related. So here you can see postsynaptic cell and two excitatory presynaptic inputs and one inhibitory input shown by the negative sign. So now, if you stimulate the excitatory presynaptic input twice, but with a large interval. So they produce some excitatory postsynaptic potential. But the second one did not make any difference. It also produced similarly. But then if you reduce the time lapse between, then so you see these two arrows are close by. Then you the effect is summated or added up, and the threshold is reached. And threshold reaching will result in the action potential. So now this is temporal summation. Why do you call it temporal summation? These inputs are coming at depending upon a time interval. Time interval is what is producing this effect or not producing the effect here and producing the effect here. That means from the same source, but at two different times the inputs are given. If the time between them is very little, then it causes the summation, temporal summation, and produces the effect. Now, if you see for the spatial summation, EX1 excitatory excitatory input 1, excitatory input 1, excitatory input 2 is in the black. So if you give an excitatory input from the 1, you got a EPS. Similarly, if you stimulate the EX2, then you got another EPS. There is no summation. But remember this is one source, this is another source. Now, use the same input sources EX1 and EX2, EX1 and EX2 together at the same time. Okay, so though they are coming from two different sources, they still produce summation and raise the threshold and causes the action potential. So as the inputs are coming from two different sources, but at the same time, you call this as spatial summation. Okay, another something related, you can even cause summation or integration. So EPSP and IPSP. Now this is plus and this is minus. So if you add them, the value will come down for the EPSP. So now EX1, this is stimulated, we got a EPSP. Now you now give a inhibitory input, you got a hyperpositive range, because both of them are given at a larger with a larger interval between them. So the EPSP is produced when the excitatory input is given. IPSP is produced when inhibitory input is given. But you give them together, if they are equally effective, then there is no effect. Each one cancelled out or integrated and cancelled out, and there is no response. So this is what the inhibition. Okay, subliminal fringe. We'll say ABC neurons, presynaptic neurons are the supplying X, Y, Z postsynaptic neurons. So you can see one branch is supplying X, B is supplying X and Y, C is supplying Y and Z. Now, the neuron A terminates on X, neuron B terminates on X and Y. And if you stimulate A and B, when they are stimulated alone, they will show EPSP. You stimulate this, this will show EPSP. You stimulate this will show EPSP, this also will show EPSP. But not sufficient to produce an action potential. And if you stimulate both A and B, then A and B, then there is summation. There's some X, then X will show A action potential. So what happens to the Y? Y is still having a small EPSP. So it is not yet reached the threshold. So it is in the subliminal fringe. So Y is in the subliminal fringe and the X is in the occlusion. So we are talking about the subliminal fringe first. And then occlusion, here you can say, you can show it more clearly if you use repeated stimulation. Repeated stimulation. So you B stimulates Y and B stimulates X and Y, C stimulates Y and Z. Okay, if the B and C are simultaneously stimulated and you are giving this tetanic stimulation, simultaneously stimulate, the net effect is less than when B and C stimulate separately. So suppose you stimulate B tetanically or repeated stimulation is given. Then X will show action potential, Y will show action potential. How many neurons? 2 neurons are showing action potential. C, similar repeated stimulation can cause action potential to Y and then action potential to Z. So again, 2 neurons here also. But then if you do that simultaneously, you only get the response in 3, not 4. So part of the effect is occluded. Part of the effect is occluded. Instead of 4 neurons, you are getting only 3 neurons. Facilitation. That is like beneficial, something like that. With several stimuli, each consecutive stimulus evokes a larger response than that evoked by previous stimulus. You know what happens if this while is stimulated one after another, they will each consecutive stimulus, the response is larger. We eliminate it, of course. Physiological mechanism is calcium channels open for prolonged period and the concentration of calcium inside the synaptic nerve increases more and more. So more neurotransmitters is released, and that causes the facilitation. Synaptic fatigue. Repeated stimulation of the synaptic neuron. This will ultimately, initially it will give a high response, but gradually, ultimately, the response and final the response decreases and also finally disappears. Response also disappears, but we don't respond. Now, when you put on a shirt, for example, initially you will find that there is a shirt on your body. After sometimes you are not really aware, or it is just there. No. So that's something like fatigue. Temporary phenomenon due to decrease in the availability of neurotransmitters at the synaptic ending, and then gradual inactivation of the calcium channels and decrease in the intracellular calcium. So neurotransmitters less, calcium is inside the presynaptic part will also decrease. Hypoxia. Hypoxia does affect synaptic activity. Synapse is more susceptible to hypoxia. Synapse is more susceptible to hypoxia compared to the nerve fiber. Nerve fiber is not susceptible like the synapse does. Reverberation. If you see these two neurons, each has a collateral ending on presynaptic neuron. Presynaptic neuron has a collateral. Postsynaptic neuron also has a collateral ending on the presynaptic neuron. So there is a reverberation of activity. This is due to networking. After discharge, even after cessation of input signal, the output signal lasts for some more time. Usually occurs with a strong painful stimulus. That means usually if you touch something, yes, as long as that fine pressure application leading to touch is there. But then, as soon as you hit a roller, there is no touch sensation. But then, with painful stimulus, noxious stimulus, then it can, particularly when it is a strong painful stimulus, then the response or the output the signal will last for some time. So you get pain even after the pain giving stimulus is stopped. Synaptic plasticity and learning. Plasticity itself is the capability for change. So the changes will help in learning process. Synaptic transmission can be increased or decreased due to past experience. So from the past experience you learn. So it leaves an imprint on the network. Post-circuitry potentiation, long-term potentiation, synaptic fatigue, habituation, sensitization, low frequency depression, etc. are the various kinds of synaptic plasticity. Post-circuitry potentiation, application of stimuli to presynaptic neuron. If you give, say, 100 single stimulus per second for 2 seconds, you get a response. Second stimulus will evoke larger response due to increase in the intracellular calcium concentration in the presynaptic part, and then calcium improves the accuracy. Long-term potentiation, and the post-technique potentiation is long for days. Here it is very long, it is very short-term duration, and here it is a long-term process. And the post-technique potentiation is prolonged for days, and for a long-term potentiation. Due to increase in the intracellular mechanism is similar. This occurs in the hippocampus, and the hippocampus is one of the necessary parts of the brain that are taking part in the memory, learning and memory. Sensitization. Prolonged increase in postsynaptic response after stimulus is paired with painful noxious stimulus. Now, earlier the same thing was producing a potentiation. Now, this is sensitization. If it is associated with pain stimulus, oxygen stimulus, then the prolonged increase in the postsynaptic response. So basically, presynaptic facilitation, like what we have seen earlier. Renshaw cell, now we come to inhibition. Renshaw cell inhibition. Renshaw cell, it is the alpha motor neuron in the spinal cord. Spinal cord is the spinal cord has the soma of the alpha motor neuron. Then this is the motor nerve fiber. If it gives a collateral to another, this occurs in the spinal cord itself, and this small cell, short cell, is the Renshaw cell, and this causes inhibition, what you call Renshaw cell inhibition. And the neurotransmitter here is the acetylcholine. So now, with a Renshaw cell like cell, inhibitory cell in between, you can produce a direct postsynaptic inhibition. This is the postsynaptic inhibition. Directly, this inhibitory neuron produces inhibition of the motor neuron. But now, this one causes excitation, and this neuron is ending on the axon near the axon terminal of the axon. So this one, when it is activated, it causes the inhibition of this process. A less amount of neurotransmitter is released. Less amount of neurotransmitter is released. So that is amounting to the inhibition. So this we call presynaptic. Before the synapse, presynaptic part is inhibited. That causes inhibition here as well. And this is direct postsynaptic inhibition. Now, what are the various, what the importance of synaptic transmission? Overall, one-way conduction, channeling, divergence and convergence, integration, could be because of convergence and divergence, integration can happen, summation, conclusion also take part, modulation will take part, regulation, not only just modulation, but regulation also can happen related to the synaptic transmission. So that is the end of today's lecture on Synapse, which I try to cover a larger portion, including the properties, and then so I have to go fast, and then lesser amount of information was given in this particular lecture. So see the details in the previous lecture on the same topic.